Hey y'all, this is a video on the harder example of osmotic pressure that we did in class, and I just wanted to go through it. And in this video I'll be going through it step by step so you can follow along. All I have pulled up here are my problem and my calculator, and I'll give you any conversion factors you need. So this problem starts with telling us that biochemists have discovered more than 400 varieties of hemoglobin, and hemoglobin is obviously important because it is the blood protein that allows you to carry oxygen. And I've put, just for flavor, a little rendering of hemoglobin here. So we have a physician. She's looking at a new variety of hemoglobin, and she dissolves 21.5 milligrams of that hemoglobin in water. That makes a total solution volume of 150, and she is doing this at 50 degrees Celsius. And this is pretty typical for biochemistry experiments. They're small scale, kept cold. And we are told that she measures the osmotic pressure, and she measures that as 3.61 torr. We are asked, what is the molar mass of the protein? So we have to consider that we need to remember to use the formula for osmotic pressure. Capital Pi for osmotic pressure equals MRT. And there will be some conversions here that we really have to consider. So she gives us our measurements in torr. I'm going to end up converting to atmospheres because I want my units for the universal gas constant to match up. I could use one that uses torr, but this is going to be just a lot quicker. You get to use a more familiar format of R. And then temperature, we're given in Celsius. We're going to have to convert to Kelvin again because I got to match up with R. And then finally, we will have to remember that this big M is molarity, which is moles per liter. And we already do have the amount of mass of this hemoglobin that we have. It's 21.5 milligrams. And if we have grams and we have moles, we can figure out molar mass. So the first thing I'm going to do is just do a quick little flip of this formula so that I'm solving for what is actually unknown, which is molarity. So molarity that's a capital Pi for osmotic pressure over RT. And then I can start converting things and plugging them in. So I am given a value of 3.61 torr. You may not remember this, and if you needed it on exam, I would give it to you. 760 torr is 1 atmosphere. Torrs are out. Torrs are out. And I'm going to go ahead and pop that in my calculator. Hopefully you are calculating along with me. And I see that this is 0.00475 atmospheres. I'm going to block that in. It's a number I'm going to need later. T is given as 5 degrees Celsius, but we need this in Kelvin, so we're going to add 273.15 Kelvin. Total temperature, 278.15 Kelvin. And then R, you would look at your formula sheet to see what is appropriate, but the R value in the units we're going to use are 0.0821 atmosphere liters moles Kelvin. And then we can block that in. All right. So now I can say, using my turned around format for the osmotic pressure equation, that molarity is going to be equal to 0.00475 atmospheres. I'm going to just divide by T real quick here because it's the easiest thing. And then I need to divide by R. That's the same as multiplying by the reciprocal. So just for the sake of space and my units, I'm going to write it out like this. So dividing is the same as multiplying by the reciprocal. So it comes to look like this. Now here we just want to do a check of units to make sure that we get something that makes sense. And we have to remember that molarity is moles per liter. And we look here and we see that atmospheres are out, and I also see that Kelvin is out and Kelvin is out, leaving my last units left as moles per liter. And this is something that makes sense because I was solving for molarity to begin with. You should be quite upset if your units for molarity aren't moles per liter. Something's gone wrong for you. And then I'm going to tap this into my calculator. You should be, playing along at home. And I'm going to get the same answer I got before because nothing has changed. In the world of math, I get 2.08 times 10 to the negative 4 moles per liter. This is the first half of the problem. This is maybe the hardest part here. So what we have to do now is calculate, well, how many moles was that? We already have molarity. We have 2.08 times 10 to the negative 4 moles per liter equals some number x, because we're looking for the number of moles that we had, over our volume. Our volume was 1.5 milliliters, and you're going to want to be able to convert that pretty quickly at this point. 1.5 milliliters is 0.0015 liters. We can cross multiply to solve for x. And you should also see at the same time that your liters are going to cancel out. So x will carry the unit of moles, which is 3.12 times 10 to the negative 7 moles. All right. So far, so good. We are getting a little crowded, so I'm just going to make some space. We already did this part. Luckily, this is a video, so you can always pause and go back and look at your notes. All right. So now we know something very important, which is the number of moles that contributed to the osmotic pressure in that solution. And we just have to get all the way from moles to grams per mole. So molar mass is grams per mole. I have moles. It's 3.12 times 10 to the negative 7 moles. I have to get to grams, so you have to do another conversion. We had 2.51 milligrams. There are 1,000 milligrams in a gram. So this will come out to be 0.0215 grams. We can plug this in. Our units will be grams per mole. And if you divide this all out, you're going to get a number. I'm going to round that number, and I'm going to round it to 68,900 grams per mole. Now you may be saying, whoa, that's a huge molar mass. It is, and this is a molar mass that is pretty normal for a protein size. I'm okay with this. Proteins are, the largest molecule we've probably looked at so far. We're not doing just little molecular molecules where you're calculating it off the periodic table. This is much, much larger. If you had the full formula, you certainly could calculate it, but it would take you quite a long time. So this is the setup for this. It is really mostly logically thinking through this and keeping your bookkeeping and your unit conversions really tight. This one, it looks like you have to convert every single unit at least once, but it's a really good example of a application of osmotic pressure and a little bit of a harder problem to practice with.